We're not doing 10-4, just 10-3.
That's super duper.
Hello and welcome back to Calculus 2 for one last time. Yeah, I know.
One more week.
Calculus.
You're not going to live stream the final?
Just tears in the brain.
I should, I guess. Section is on 10.3, calculus in polar coordinates. So we get to take derivatives and integrals in polar coordinates and then call it a day.
Woo! Yeah.
So we said that we might have a cardioid, right? That would be a cardioid right there. And as you can see, cardioid is a line, so you can have a tangent line at certain points, right? So if we have polar shapes like cardioids and circles and those flowers we discussed and things, right? We can have we can still have tangent lines. Now remember that all of this is set in XY coordinate system. So this equation that we have over here, which is a tangent line, is going to be given by equation y equal mx plus b, while your equation over here is given as r equals function of theta. And the point of tangency is given as r theta. So we have to work in both worlds together to come up with this stuff. So what you hopefully know is that the slope, so in Calc 1, slope is given as the derivative computed at point A. Now derivative is better written as dy over dx. That's a Leibniz notation. And you say you compute this at x equals to a. So that notation, just like for your definite integrals, right? When you do integration and then you put the vertical line and you say between 2 and 7, right? So now you put the vertical line and you just put on the bottom x equals a, meaning compute at a. Good effort. So now we see that the derivative, right? We have to be able to find derivatives. So given some function r equals f of theta, right? Given some function r equals f of theta, we need f prime of x, which is dy dx, right? So now, what do we know? Well, first off, we know that x is given as r cosine theta, and we also know that r is function of theta. And we also know that y is equal to r sine theta. So if I differentiate these in respect to theta, I will get dx d theta and dy d theta. And simply to get what I need, which is dy dx, I need to divide dy d theta by dx d theta. D thetas will drop off and you just get dy d theta, which is the derivative. So all I need to do is to find the derivatives of the conversion formulas between the two realms, find the derivatives of those conversion formulas, plug them in, because again, what do you have? You have derivative of y divided by the derivative of x in terms of theta. So, what are these derivatives? Well, we'll start with the derivative of y, because that goes on top. So, if I start with y equals r sine theta, I'm going to rewrite this as f of theta sine theta. So, the reason why I'm rewriting this is to make sure that I see that this r is not a constant, it's a function in respect to theta, so that I am actually doing what I have to do, and that is a product rule. So to find dy d theta, I have to do the product rule, copy the first times derivative of the second plus copy the second times derivative of the first, which is f prime of theta. So that's that part. Now I have x equals r cosine theta, which is equal to f of theta cosine theta. And to find dx d theta, I do the product rule there. So copy the first, which is f of theta, times the derivative of the cosine, that's a negative sine theta, plus copy cosine theta, and then f prime of theta. To put these together, I'm going to list the f prime terms first, because the one in the denominator has a minus, so I just don't want to put minus first. So what is my f prime of x? Well, f prime of x is given as dy dx, which means we just divide dy with this. So, and I said start with the derivative term first. So f prime theta sine theta plus f of theta cosine theta divided by f prime theta cosine theta minus f of theta sine theta. Here's your formula that will compute the derivative of the polar equation, but the derivative is given no copying in Cartesian, right? So dy dx. Why is it not a simple equation? Because we are working across two different realms, right? Your equation that it's given to you is given to you in easy terms, which is r theta, right? Because it's built for polar coordinates. But then you want the dy dx out of it, right? That's why it has to be crazy. The derivative in theta is just derivative in theta. It's just simple, right? But if you have to jump to a different coordinate system, which is what we are doing because we want to find the derivative, to find the tangent line, right? We have to jump through these hoops. So let's find a tangent line to one of these formulas and have everything so this is that cheap part, right, when you do this. Integration is next, yes. You have to memorize the formula and then good luck with the rest. Is this book gonna work or just go home?
That's it?
I'm trying to get to... The book won't load.
And class is over. All right. I think my twin brother going to take a class with me.
You have twin brother?
Yeah.
I have to meet him.
Identical too, bro.
Really?
Yeah.
Does he say my boy?
No.
No? Then it's not identical. It's not gonna be the same.
He doesn't have. He speaks like a lawyer.
Aww.
That's where I got allegedly.
That's what I get allegedly.
No, I'm kidding. If I had a twin brother, I would have ate him in the womb.
Yeah. It's pretty much like Highlanders. Yeah, exactly. There can only be one.
Let's do the Highlander. I don't even know what that means.
Dumbass NJT student.
Huh?
He's in Rutgers.
Yeah, he's a Highlander.
I'm a Highlander.
Or Highlander. Yeah, the Highlander. The computer pipeline.
I didn't say anything.
The Highlander pipeline.
You're a Highlander. You're a Highlander.
I know NJT.
What?
NJT, right here.
Yeah, I know. You keep saying it. You're a professor, man. Big professor, man.
2 years. Well, a year and a half.
Where'd you study?
My boy,
Where'd you go to
accelerated.
professor? You didn't like it there?
Relax. The book. Oh, there's the book.
Relax, man. I hear him.
Relax.
No questions from that side.
Every day is just
Yeah, no questions on this side of the room. The short answer is no, but then there is more to it. Yeah, I don't know. This thing is. I think the website just exploded or something.
Too many files.
All right, so let's make up a problem because such is life.
Whoa.
my boy.
What do you say? What do you tell him? Calm down.
He was like, relax.
So find the tangent line.
So savage.
To r equals, let's go with the flower. So 3 cosine 2 theta at theta equals pi over 6, whatever. There we go. All right. So we have the equation, guys, r equals f of theta. The procedure is the same. You have to find the derivative first. Well, just crank this and then compute that at theta equals pi over 6. So dy dx is equal to, let's say it's going to be enough, f prime of theta. Well, that's just basic derivative. Derivative of cosine is negative sine, so I have negative 6 sine 2 theta times sine theta plus 3 cosine theta times cosine theta. Maybe we didn't need the line that long. Generally, when these problems start, I'm like, okay, start a new notebook, but f prime of theta again, which is negative 6 sine 2 theta times cosine theta this time, minus the something, 3 cosine theta sine theta. Now, when you plug in theta equals to pi over 6, the dy dx changes into m. So, m is equal to, good effort, nice. We have negative 6 sine of pi over 3 times sine of pi over 6 plus 3. And in parentheses over here we have cosine of pi over 6 squared, because it's cosine times cosine. Now, on the bottom, negative 6 sine pi over 3 times the cosine of pi over 6 minus, and now we have 3 cosine pi over 6 sine pi over 6. We could have combined it, whatever. So this is equal to, m is equal to, now start a new line. Sine of pi over 3 is, very good. And then sine of pi over 6 is, very good. Plus 3 times cosine of pi over 6 is, very good, squared. Divided by negative 6. Sine of pi over 3 is, very good. And then cosine of pi over 6 is, Oh, wait. On the top, that was sine of pi over 3 and then sine of pi over 6. No, it's good. Cosine of pi over 6 is? Very good. Minus 3 times cosine of pi over 6 is? Very good. And then sine of pi over 6 is? Very good. All right. You got all of these. That's good. So all you need to do now is to compute all of this. Now see that 6 kills these 2 and 3, and then over here 6 kills 3. So some stuff simplifies. We have negative root 2. 3 will kill one of the 3's, so we have root 2. That's 2 over 3, so plus 2/3. And then here we have negative 2/3 minus 3 root 3 over 4. Well, that's that. And then what do we talk about? Then we're going to do times 12 to kill all of the double fractions. So I have put the fraction first half of this is 4 times, so 8 minus 12 root 2 divided by, and on the bottom I have, actually, no, I'm going to keep it because I'm going to, oh, I'm sorry, then we're going to go back to 8 minus,
do the right thing.
8 minus 12 root 2, because he can erase, that's fine, I'll leave it that way. And then in the denominator we have, well, he said so.
Nah.
And then we have 12, so that's negative 8 minus, and that kills that, that's a 3, that's a 9 root 3.
Is that the right answer?
Yes. So now we are going to, we're just going to quit. That's,
Thank you.
so let's call this as, it's, actually, no, let's go on.
Stop playing.
So 12 root 2 minus 8 divided by 8 plus 9 root 3. There we go. So call this.
We can do that. Yeah, we can do that.
Multiply top and bottom by negative 1, right? All right, so we have our slope. Now, the question is, what's the rest, right? We need to find b. Now, to find b, you have to have a point x and y. Now, what's x and y?
We know it.
We do? Yeah, we do, right? We have,
Heck yeah.
yes, we have to plug in. So now we have that r is equal to 3 cosine 2 theta. And theta is equal to pi over 6, right? So if, nice. So if theta is equal to pi over 6, we plug that in. R equals to 3 cosine pi over 3. Cosine of pi over 3 is 1/2, so it's 3/2. So our point that we have is r theta, so 3/2 and pi over 6. So that's what we have. Welcome. So now we have a point, and we need to convert this point to x and y. So now we know that x is given as r cosine theta. R is given as 3/2 cosine of pi over 6, which is 3 root 2 root 3 over 2, which is 3 root 3 over 4. And y is r sine theta, which is 3/2 sine pi over 6, which is 3/2 times 1/2, which is 3/4.
This is obviously not going to be on the exam because you just taught it and this is not enough time for us to know this in one day. And it's going to be
You already know all of this. You just got messy calculations.
everything you're saying is alleged.
Cadowitz did it.
So now,
It is, but
so
I thought you was better than calculus.
So now what we do here, guys, focus. All we need to do now is just to say y equal mx plus b, and we're done. So y is 3/4, m is 12 root 2 minus 8 over 8 plus 9 root 3 times 3 root 3 over 4 plus b. Nice.
You're a mean person.
How do we do this? You calculate that or partial fraction?
Everything is partial fraction to you. So now we can cancel the 12, 8, and the 4 by 4 and get a 3 and a 2 over here. That's good. So now that's... You divide them by 4, right? Yeah. So 4 and there, so that's 3, so that's 9 root 6 minus 2 times 3, 6 root 3 divided by 8 plus 9 root 3 plus b. There we go. So b is equal to 3/4 minus 9 roots is just our arithmetic. 6 root 3, 8 plus 9 root 3. This is
Disgusting. This is awful.
so all we need to do now is to rationalize, find the common denominator, and then, or we can just write it out. I understand. Why are you complaining? This is arithmetic.
It's already a
This ain't a arithmetic class. It's a math class.
I know. So we could combine this, or we could just say, okay, y equals, and then just write what it is. 12 root 2 minus 8 over 8 plus 9 root 3 x. So this is y equal mx. And then we have plus b, which is 3/4 minus 9 root 6 minus 6 root 3 divided by 8 plus 9 root 3.
In this graph, I feel like at this line,
Like this.
I guess you're right.
Because I am.
Just a positive slope.
It is a positive slope, yes.
That's what it is.
It's very good. It's positive slope because 12 times root 2 is bigger than 8.
Yeah.
So it's a positive slope. It's just a line. You can go and you can work your decimals if you love decimals. You can come up with some kind of decimal answer. The book wouldn't load, so I picked whatever example, and this is what happens when you just make up stuff out of nowhere. So there you have it. It's a very straightforward procedure where you use the formula to find the derivative, and then good luck with your calculation. Right? That's technically what it is. Now, please observe the steps that we took to do this. So, step number 1 is to find the derivative using the formula. Grind it through calculations to come up with slope m. And now this is the new part which you never had to do before. Because before you are given x and a y, so you just plug that into y equal mx plus b and you find your b. You don't have x and y now. So we have to go through the extra hoop over here to figure out x and y. And then you have your y, you have your m, you have your x, right? And then you can calculate b. So that's exactly what happened here. As you can see, I plugged in y equal mx plus b. Here's my y, 3/4 over there, right? And then here's my m, which is the calculated slope. Here's your x, 3 root 3 over 4, and then plus b. So now I should have gone through more algebra to actually combine these b into a single expression. Let's not flip here. How about that? So it is, I would say it's a very straightforward procedure. It's not something that is hard at all. It's just long and annoying, and it takes a lot of focus to get through these calculations. So Step number 1, get the derivative, compute the derivative. Step number 2, get x and y, because you don't have them. And then step number 3, calculate b, and then you have your tangent line. So that would be calculation for derivatives. As in Calculus 1, derivatives are computing the instantaneous rate of change, so they compute change at the point. And you can use that if you have, let's say, an equation that shows how much is stock price varying per day, per hour, per month. So whatever the unit is, the derivative. See, when you say change in a price of a stock in a day, right? But you are looking at the graph that displays 10 days or a month or whatever, right? The entire day, which is 24 hours, is going to become a point, actually, and you would say that you gained or lost amount of money, which is actually the slope, which is the change for that one day. And guys, when you are looking at the stocks and things, they do have that little red arrow or a green arrow that shows how much the stock is growing or how much the stock is falling. So let's see.
Got a nut, bro? Got a nut, bro. Just texting me now. Can't just talk.
All right, so here's... so we're going to take
Yeah, I got plans tonight.
5... Let's take a look at the daily. You can't see it. No call. So if this is lows, it doesn't matter what you pick. So if you take a look at lows, you see the red arrow over here, and you see that they are losing. So at this point, right, 1.6% down. Right? And if you take a look at 5 days, you see also downward trend. If you take a look at 1 month, again, downward trend. 1 year, right? So you see, if you take a look at a year, if you take a look at a 5 years, right? So you have to be, right, when you do these kind of things, you can't just consider locally, right, what's happening. So if I was to ask you, you know, good or bad, everyone's gonna go bad, 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 because, right? But if you consider what happens over here, right? $1.50 of a loss per, right? But if you just take a look at 5 years, over here it was $44. On the other end is $94. So that's $50 difference per stock in, you can do the max. So $50 over 5 years, the stock increases, right? So we can say, okay, it's the $10 growth per year if you average it out. And then, obviously, if you had 10,000 shares, that's $500,000. So this is where you play this game, and the people who don't know, like if you want to go and get the stocks and stuff, you're just going to lose it all, because if you're not looking at what technologies are coming up and emerging, you don't know the news, you don't know the need, you don't know the market, right? You just have $1,000 that you saved at your restaurant job, and you say, with this $1,000 I'm going to invest, and the stock market is going to double, triple, quadruple, and then I'm going to have millions of dollars by the time I'm 37. No. What you're going to do is you're probably going to invest those $1,000. It's going to burn because you have no clue what the hell you're doing. To do the startup. So, you know, people that get lucky, right, to shoot in the dark and they get it, yeah. But people who are investors and who actually make money from money, they are very smart and very careful, right? They have very careful analysis and they know a lot. But this is the way that the stocks work. So if you bought the stock, you bought 10,000 shares, what do you have? 10,000 shares and what, at $44? So 10,000 shares at 44 bucks. So how much money did you put in? Huh?
Oh, 440.
No, let's do the 1,000 shares. 1,000 shares.
I don't want to be stupid. I was like,
So, if you do 1,000 shares at
$44.
44 bucks, right?
Yeah.
So you have a 44K that you invested. That's your investment. Lowe's takes that money and they buy their stock. They open new stores, they get more people, more stock, more stuff. Right? That's what. So the difference is that you make is 50K. Yeah? All it did is just let it sit. Right? But then you have companies that take the nosedive. The corporate policy was not good, the fraud, the this, and that, right? That's why people get very, very annoyed when the companies are doing something they're not supposed to do because they lose all the money. So the derivatives would measure these instantaneous changes. So if you know how to take your derivatives, you'll be able to follow these kind of things. That's one of the applications. Let's talk about integration.
Ooh.
And that will be it.
Ooh.
Ooh.
Out two. Yo.
You get millions of dollars from the stock.
Don't worry about it.
Yeah, Nick's got small business in the back.
Wow.
Dude, you see where that
I want
spike
you to
below
be
at the
my
beginning of the
contact
year?
man.
Dude, that's right where he was.
Your
Why
value.
did you
Make
think
your
it was
value.
low? Oh, I should not worry about it. I thought we was first.
You got them Swiss bank accounts? Mr. Nick,
Did
did
you
you own
own
Estonia today when it went up like 5%?
Don't worry about it. So now we're going to talk about integration. Right? You want to integrate your. I'm sorry. As I said, don't worry about it.
He's trying to get rid of money. He bought all his money on Bitcoin. It's over.
Yeah,
It's
no.
over, yo.
This.
Like cryptocurrency just being alive.
Oh,
Just get it like every.
can't see it. Now you can see it. There we go. This is a circle. Is that better?
It looks like Iron Man shield.
How's that?
That's the circle in Minecraft. This is the circle in Minecraft. Ask Alex, he knows all about it.
That is a circle of Minecraft, though.
Exactly. So my circle infinitely better.
It's actually better.
This is a circle. If you don't think so, you should go check your eyes because something wrong.
It's multiple circles, my guy. There's multiple circles. Relax.
X and Y. Equation, so let's call the capital R. An equation for this circle would be x squared plus y squared equals to r squared. So this is equation of the circle. Now,
See R again?
R. If you want to find the area under this circle, you can integrate one quadrant of the circle and then multiply by 4. So to use Calculus 1, you would go.
That's his excuse for teaching us this so late.
You would take the integral from 0 to r, and you would integrate the equation r squared minus x squared dx, which is clearly a trig sub. So if you want to find the area of the circle, you would have to do 4 times this integral, and for the integral you would have to use trig sub, because you are integrating, let's say, 16 minus x squared under the radical or something like that, right? So not too much fun. Now, what do we know about polar coordinates and circles? We know that if I have, let's say, x squared plus y squared equal to 16, the polar representation for that particular equation is just r equals to 4. Much easier equation in polar world. So, if I use the equation for the area in polar coordinates, which is integration in polar coordinates, this integral should be a joke, because the input equation is a joke. And this is the reason why we want to learn polar coordinates, because something that is hard and annoying to do in the Cartesian system, polar coordinates should provide us a very easy alternative. So, here is the formula. Area is equal to 1/2 integral alpha to beta, because we are using angles now, right? It's going to be d theta. And then you have your r squared d theta. So this is your equation to calculate area in polar coordinates. So area in polar coordinates. This is our equation. Now, again, I'll write it in blood over here, that r is f of theta. So this r is not a constant, this r is a function. So if I want to find the area of that flower that we did the derivative for, the 3 cosine 2 theta, the entire 3 cosine 2 theta is getting squared inside the integral. Becomes 9 cosine squared 2 theta, and you go from there. So now, if I am to unleash this formula upon our circle equation, so circle r equals to 4, which is actually the same as x squared plus y squared equals 16, I will have that the area is equal to 1/2 integral 0 to 2 pi, and then I have 4 squared d theta. So what is the integral there? Well, the integral is 1/2 of 16 theta computed from 0 to 2 pi, and that gives me 16 pi. Does this make sense? Well, hell yes, because you know that the equation for area of the circle is pi r squared. If your r is 4, well, that's 16 pi. We have the same answer, right? So, well, we have to talk about mechanics of how to set up and deal with the integral, but this is the cheapest problem that you can get. Polar coordinates are designed to work in circles and with round objects. Therefore, the equation for the circle is going to yield the easiest possible integral for you to solve. Easiest possible integral for you to solve. Because what is the circle in polar coordinates? It's constant. So what's the easiest thing to integrate? Constant, right? So integral of a constant, it's a constant squared here, right? Because of the equation is r squared. So when you plug all of that stuff in, you get 16 pi, which is actually area of the circle. Now, I'm not expecting you actually to do this with a circle, because you know the formula from 2,000 years ago, right? But it's a good, mathematical gymnastics to see that these things actually work. Now, if I ask you to do the area of the cardioid or the flower, you will have to use this, which is actually what's on the test tomorrow. Yes?
In that last line where you compute the definite integral,
yes.
If you get 16 theta and 2 pi is the limit, how does 16 times 2 pi turn to 16 pi?
There's a half in front.
Oh.
So it's actually 8 theta.
Your glasses are cold.
Yeah, put them glasses.
Oh.
Yeah.
You cold in your chest.
Yeah, dude,
Would
this thing is crazy.
with an example probably this would be able to find the equation for
Equation is always given to you, right?
so you give us what r equals and plug what that equals.
Yes, because I'm going to ask you to compute the area of the cardioid, or the flower, or cardioid flower.
And it would all be the same formula? We just take the
Yeah.
equation and plug it into this and
Well, that's unless you have two objects that are intersecting, so you have
the minus and the equal. So it's the same, we just set them equal each other.
I will talk about it now.
Super.
Jeez. So
The next
it's not so bad though.
part is to find the area of the flower that we have, the cosine flower that we had earlier.
Which is on the exam tomorrow.
Which is on the exam tomorrow, yes.
What's the flower?
Or the cardioid, or the circle, or combinations of them. Depends when I get to leave, so I have time to write the exam. So, guys, here we have r equals 3 cosine 2 theta. This is your flower from yesterday. So it graphs on the that it looks like that. And as you can see, we talked about this when I did the polar graphs. I said even number in a cosine, even number is doubled to give you the number of petals, and odd number is what it is. So cosine 5 theta has 5 petals, and cosine of 4 theta has 8 petals. So even numbers double, so 2 is even, 2 times 2 is 4, so 4 petals. And odd numbers have the amount of petals that it's written. So 3 theta gives you 3 petals. So that's that first part. That's something that you should know. And now the question is, what is the area of this flower? Because clearly when you see a flower, you want to paint it, right? That's what we do as humans. We improve nature.
I know I do.
Yeah. So what am I going to do now?
It happened right there.
You just take the integral of that.
Exactly. A equals. Now, guys, there are some subtleties. So this is 1/2 0 to 2 pi. Why is it 0 to 2 pi? Because I want the entire flower. What is the integral if I want 1 petal? You have to be careful with the limits. Now, clearly, 1 petal you would know. Calculate the whole thing, divide by 4. Right? There should be common sense. But you can't exercise that for cardioids because cardioids are not radially symmetric. Flowers are radially symmetric. So you can calculate the entire thing. Like for the cardioid, that doesn't work. Because if the cardioid looks like this, and I want the area of this part over here, that's clearly not the half of the whole thing to go, calculate everything and divide by 2. It doesn't work. So you can't always do that trick. Now, I want the area of the entire flower, so entire flower is 0 to 2 pi. Anytime you're looking for the whole thing, you will always go 0 to 2 pi, because 0 to 2 pi draws the entire object once. So 0 to 2 pi is cool. And then we want to take our 3 cosine 2 theta and square the entire thing because it's r squared. And then we have d theta. So now, to calculate this, we have 1/2 integral 0 to 2 pi. 3 squared is 9, so it's actually 9/2 outside. And you have your cosine 2 theta squared d theta. What is the only way to integrate? Yes?
The half angle thing?
No, the half angle. I know you're thinking the right thing, you're just saying the wrong.
It's not called power reducing.
It's called power reducing, yes. You're going with the power reducing, you're going from a squared to no exponent. That's why it's called power reducing. You can actually flip that formula into half angle formula, yes. You have to do substitution to actually make it into half angle.
Are we doing like 1+?
Yes. So 9/2 integral 0 to 2 pi, and then, right, as Harry said, it's 1 plus cosine 4 theta. Right? Because you started, no, this is the biggest 4 you've ever seen.
I don't think I counted the 4.
That was
barely more.
So, guys, if your formula for power reducing is starting at 2 theta, you must double And this is where the gray dies most of the time, right? Because you will always have some number of petals. You are not going to get a flower that just says sine theta. That's one petal, let's say, right? So if I have a 12-petal flower, well, that's sine or cosine 6 theta. That means when you do the cosine over here to compute, you have to square it, which means it will become 12, right, when you do this formula. So now you have this, and it's equal to 9/2, and then you have the integral of 1/2 is 1/2 theta, and the integral over here is the integral of cosine is sine, so you have sine 4 theta divided by 8, computed from 0 to 2 pi. Why is divided by 8?
1 over 8.
Because, yes, that 4 is going to use the u sub, right? It's going to come out as the over 4, and you already have over 2, so that's over 8. So now, sine will die at 0 and 2 pi, so you are left with 9/2 pi as the area of the entire thing. Yes?
One question. Would you be able to just take out the 1/2 so it's 1 plus cosine before theta?
Yes, and you have 9/4 outside. Sure. It's going to give you the same. Anything else? Yes?
How do we know what theta should be?
What?
What the upper bound should be?
As I said, that's the next topic. Yeah, that's next. So now we're talking about that.
Okay.
So the question was to compute the area of the entire flower. I said 0 to 2 pi traces out the entire flower. Therefore, we use 0 to 2 pi because I wanted the entire flower. Now, more interesting questions are those where we do not want the whole thing, right? Sure, when I go to a party, I eat entire pizza pie. I mean, that's given. But then when you civilians go to the party, you have 1 or 2 slices.
Are you the guy that eats the whole pie?
Yes.
You only had 3 donuts.
Don't worry about it. I had 2 dinners before that.
Jeez.
So now, what is the area of the single pizza slice, or what's the area of 3 pizza slices, or right? Now, clearly, you take the circle, you divide, right? And you can get that way, but we can also use calculus. Let's say someone at the party is confused, right? And you you immediately use polar coordinates to explain. Exactly. Let me simplify. So you look at. It's called distraction. By the time they go and then they just walk away.
Get more pizza.
Exactly. I work these things out, guys. So here is the large pie. Here's the large pie. It has 8 slices, and we want to find the area of a single slice. Now, the common sense way that everyone should do this problem is to use the formula from 2,000 years ago, figure out the area of the entire pizza, and divide by 8 for a single slice, then times 3 if you want 3 slices, and so on. So, what is the radius on the large pizza?
9 inches. It's 18 inches.
Oh, yeah.
18 inches. Okay, so 9 inches on the radius.
Yeah, what do you know?
He said 9, that's it, sold. First come, first serve, we know how the business is done. Now, 9 inches on the radius. So what is the area of the single slice? Well, every middle schooler should be able to tell you that the area of the entire pizza is 9 square pi, which is 81 pi. And then to get the 1 slice, you will get 81 pi divided by 8. And that would be the exact inches squared for this. Now, you actually want to know that if you are an engineer working for Domino's, because, you know, the amount of topping that it goes on. You're laughing, guys. Do you think that these corporations just throw the stuff on,
Yeah.
they calculate exactly how much, because one pepperoni that is 1 cent on 100,000 pizzas, you get the idea? Per month. Do you honestly think it's just like no? This is all carefully calculated, because anytime you have anything that is done on a huge quantity times a small thing is still big. Right? So that's the rule in mathematics.
That's why they're so stingy with all this toppings.
Oh, yeah, exactly, because they're making 100,000 pizzas. So each little bit from each one adds up over.
That's why it's never right. Always never right.
Can we have this on next time?
45 minutes.
All right, so now, guys, how do I calculate this? So you're at a party, right? This is worked out, and the person's confused, right? Immediately, polar coordinates. So the 1/2 integral, and now this is the game that we play with limits, because you want one slice. That is going to be 0 to pi over 4. Because here is your 0 level, here is your pi over 2, so one slice halfway through is pi over 4, and you are dealing with pi over 4 limits. So these are your alpha and beta that you talked about earlier. Now, do I want 3 slices? Sure. 0 to 3 pi over 4 for 3 slices. 0 to pi over 2 for 2 slices, 0 to pi for 4 slices, and so on. So you can actually pick the amount of slices. Even though you can do this, make it a kid's pie. So now it's 0 to pi over 8. Right?
As well.
Exactly. So now we have 9 squared, right? We have to square the r. Now r is constant because it's circle. And even though I know that there should be a company that makes kind of square pizzas, which is weird, but whatever. And then we have d theta. Guys, we better get 81 over 8 pi, otherwise...
Math is broken.
Yeah, exactly. So this is 81 over 2 on the outside. Integrate 1 to get theta from 0 to pi over 4. When you plug in pi over 4, you get 81 over 8 pi inches squared, and all of the confusion is... Yes.
You're like, yeah.
Exactly.
This is obviously
Well, of course, if they don't understand the formula that was developed 2,000 years ago or more, well, clearly the newer stuff will make more sense. So, let's see if...
Now you sound like Kanye also. You know a rapper went on a track.
I'm sorry, I wouldn't know. All right, guys.
The first part sounds good.
Now you are faced with a shape that looks like this.
Ew, I don't like that.
With a question, what's the area?
Good question.
Right?
That's
So,
the Champions logo.
so you're looking at this and you say, well, I could you maybe use parabolas and things to figure this out, but there is a much more interesting and harder way to do this. So how about if I take a flower
Is this how you be thinking?
and then you put the circle And you see that this part over here is exactly what you're looking for. Exactly. You see, you can have infinite fun with these things. So now we're going to draw this nicely.
I need 6 more weeks of Calc 2.
But another 6 weeks of Calc 2 just for this problem.
And then anxiously await.
All right, so let's take a look at.
Just to get the crust.
So,
Calculating the crust.
so we have a circle.
Jesus Christ.
Jesus Christ.
That's too fucking funny.
It's Calc 2.
Exactly. All right. So here we have our equations. I'm going to put the circle to be r equals to 1, and r equals to 1, and then I have the flower to be 2 cosine 2 theta.
That's easy.
And I am looking for the area over here. You are used to the idea of area between two curves where you go top function minus the bottom function, right?
Yeah.
Right. Now, what we are going to learn here is that we are going to have what I like to call, instead of representative rectangle, we have a representative pizza slice. So, the representative pizza slice will go from the center to the edge of the outside, right, the function, and you see that inside function is crossed as well. So, what you have is the outer R, that's R2, and the inner R, R1. So when you are intersecting two polar functions, the best way to remember this is far minus close. That's the way to remember it. Not top minus bottom or stuff, because it could be anywhere in the polar region. So when you draw this representative pizza slice, which is the ray you extend from the origin, in this case, you start from here. I'm going to erase it. Going to start here and then just shoot this way, right? You go far minus close. So when I am setting this up now, I will go with the integral. I don't know my alpha and beta. There is 1/2 in front. I will go far, which is 2 cosine 2 theta squared, minus close, minus 1 squared, all of that d theta. You are used to this, guys, because you had your washer method. You had your area between two curves with the f minus g, top minus bottom. So this concept is not new at all. Not new. And you will have this again in Calc 3 with 3D surfaces, where you're going to go top z minus bottom z when you intersect two three-dimensional objects. It is just a universal thing in mathematics. Study the form, not the example. So what you have here, that's the area. Now clearly the issue is alpha and beta. If you observe carefully, alpha and beta are angles that happen at the intersection of the two functions. So the angle over here is angle alpha, and the angle over here is the angle beta. Now, the way to find those, again, no surprise, you are going to use your basic knowledge of solving trig equations. Because those two lines intersect when the r's are the same. So you will, so let's do it in blood. The alpha and beta limits are at the intersections. So we equal to our equations. Great. My one equation is r equals to 1. My other equation is r equal 3 cosine 2 theta. I said these guys equal to each other. No, sorry, not 3. 2 cosine 2 theta. 2 cosine 2 theta. There we go. So now, what I get is 2 cosine 2 theta is equal to 1. Cosine 2 theta is equal to 1/2. So from here, 2 theta is equal to inverse cosine of 1/2. Now, that's pi over 3, right? Right. So inverse cosine of 1/2 is pi over 3. So I have 2 theta is equal to pi over 3. When I divide both sides by 2 to get the theta alone, I get theta is equal to pi over 6. That's 30 degrees. So a little bit of common sense when you use your eyes to look at this thing. You see that the blue line on beta is 30 degrees. That means that the blue line below for alpha is negative, thank you, negative pi over 6. So now we have our limits. This over here will be your beta, and then by common sense, alpha is negative pi over 6. So what's the area? It's going to be 1/2 integral negative pi over 6 to positive pi over 6, and then you have this mess inside. This is 4 cosine squared 2 theta minus 1 d theta, and then you go from there. Does it make sense? So what you are remembering for these more complicated cases, and it doesn't matter what we are intersecting, it has to be far minus close. Far minus close. So when you draw your representative pizza slice is going to shoot through both of the equations, and it's going to touch one function first and then the other function. Now I like the example that, so this is equal to, and I'll just do it because you should be able to deal with Calculus 1 integration at this point in time. I want to explain one really cool problem they have in the book. They are intersecting cardioid with a circle, all right? So, and it creates 3 regions. I would like to know, what's what. So, the way they have this is there's a circle sitting at the origin, and then they have a cardioid that wraps around. So we have a circle, and now cardioid goes out. There we go. Now, in the book, they're asking you to compute the blue area over here. Right?
Yeah, you a little kid, dog. Get over it. Yes. I'm the littlest one here, dude. The littlest one? How old are you? I'm like, I don't know. 18? You turned 18 yesterday, dog. So you must be in this one. So I'm close. She's not making butt comments, though.
All right.
And she's actually smart.
So what do we have over here? We have the cardioid, and the cardioid is going to be r equals 1 plus cosine theta, and we have a circle r equals to 1. So these are the 2 equations, and the question is, what is the area over there? So what do you have? Well, clearly you have a circle minus cardioid. You see the circle is far away, cardioid is close by. So I'm going to have to set up this area integral of 1/2 integral, whatever alpha and beta are, those are the numbers over there. We are going to have circle, that's 1 squared, minus the cardioid, 1 plus cosine theta squared, all that d theta. So circle is far, cardioid is close. You guys are looking always at the origin, right? That's at 0, 0. And when you draw a representative pizza slice, let's go right there, right? Representative pizza slice, you see that it cuts through the cardioid first and then stretches to the circle. So far minus close is circle minus cardioid. On the other side, in orange, now this is not presented in the book, but that's the reason why you pay me $1 million to do this, is to write the 1/2 integral alpha to beta for the other side. Now, other side is cardioid minus circle. So it's going to be 1 plus cosine theta squared minus 1 squared and everything d theta, because again, here is the representative rectangle going this way. You see that representative rectangle hits the circle first and cardioid second, so it's cardioid minus because far minus close. Far square minus close square. Bueno? Why do you have to know this for Calc 3? If you're going into Calc 3, you are going to build a three-dimensional object on top of this. So this would be your base, sitting on XY plane, which is your floor, and you are going to put up walls like a stencil, like a cookie stencil, going up in a z direction for cylindrical coordinates. So this is your base. You might have two round objects, sphere-like objects, intersecting in space, that when you shine the light on them, cast a shadow like this on the floor. You are dealing with cylindrical, with spherical coordinates in that case. So both spherical and cylindrical coordinates have polar coordinates as their two-dimensional base to build three-dimensional space. So you have to know this stuff. Otherwise, in chapter 13, you're done. That's pretty much that. So your parametric equations, which is 10.1, will be used in 3 out of 4 chapters. So 10.1 will be used in 3 or 4 chapters in Calc 3, and then polar coordinates will be extensively used in chapter 13. Now, chapter 13, guys, it is going to have a section 13.3 that is going to repeat all of this and then add to it. It's going to be a two-dimensional polar integrals. It's going to do what we did today and then add double integration on top of it, so you can actually do some of the 3D stuff there as well.
Calc 2.
Done.
Done.
Hop done. Bye.
Just gotta pass.